All righty, here we are back again. Last time we talked about how to do U-sub, right? How to do substitution. But we focused our attention entirely on indefinite integrals. And that's nice. That's a good way to start that material. But the real good shit comes when you start thinking about definite integrals. And I've just had one hell of an office hour with a bunch of my Calc 2 students who are working on some legitimately hard problems about finding the length of a curve. And they were setting up these definite integrals. And a lot of them required somewhat sophisticated techniques to solve. And they ran into a bunch of problems for precisely the reason I am going to explain to you today. So what I'm going to show you today, if you've seen this before, if you've taken Calc 1 or AP Calculus or anything like that before, you may have been shown one way to handle definite integrals with U-sub. I'm going to show you something maybe a little bit different. And it's very important that you internalize what I show you today in order to avoid the many hours of headaches and pain that my Calc 2 students in the office hours were just experiencing. Namely, we're going to talk about how a U substitution is really what's called a change of coordinates, and how when you're looking at a definite integral, it is not optional, but necessary to change the bounds, the limits of integration when you perform a substitution. So my goal today is to convince you that that's really important, no matter what your high school teacher or previous Calc teacher told you. They all tell these little lies thinking they're not going to hurt anybody, but boy, do they ever. So here we go. This is MAC2311. The section number is 004. We're talking about some calculus today. And the date is the 13th of April, 2022. Today, we're going to talk about substitution in definite integrals. I'm going to show you the theorem again, like we did last time. I'm not going to spend a lot of time proving the integrand part of the theorem, right? We have a feel for how to do U-sub now and what that does to the function inside, what that does to the differential. But I am going to focus on that other part of the theorem, which is changing the limits of integration in the appropriate way to suit the substitution you're making. Let me pull up your textbook here so I can use notation that is consistent with what you'll see in WebAssign. I think that is probably a good idea. Here we go. So that's right, they use U for G of X. All right. So here's the theorem. If U equals G of X is differentiable and F is continuous on the closed interval AB, then the integral from A to B of F of G of X times G primed of X dx is the same as the integral of F of U du, but now that integral is going to be done from G of A up to G of B. When I wrote the theorem for indefinite integrals, I didn't include the differentiability hypothesis, although it was implied by the presence of G primed. And I didn't include the continuity hypothesis, and there was nothing really implying that. Here, though, it's very important. Here, it's not an optional thing. Definite integrals, we know, measure area, right? So if your function has a discontinuity, like a vertical asymptote, then that area could easily be infinite, right? Think about trying to find, I'm going to turn off my share because the grade book's open. Give me 1 second. I'm going to try to find out of there. All right. Here we go. Imagine we want to find the area under this bad boy, but I want to try to like integrate it from -1 to 1 or something. Like, we're in real trouble here, aren't we? Because this function is discontinuous at 0. So if I were to try and find the area underneath the curve 1 over x squared from -1 to 1, I'm hopping over this infinite discontinuity. And that is something that can be managed, and we'll learn in Calc 2, but not with the tools we have. It requires a whole discussion on a concept called convergence. So this assumption that f is continuous is genuinely important. And I suppose it should be continuous from g of a to g of b. Let me just say f is continuous. If you want the details there, it's on the interval g of a to g of b that the continuity of f is important. And again, if you want the details for g, it would have to be differentiable on the open interval from a to b. So this is the full story for definite integrals. You'll notice that the thing going on inside, if I cover up all the bounds, I can't do it. If I cover up all the bounds, it's the same theorem that we had the other day, right? There, almost. Okay. Good enough, right? Same theorem, just now there's bounds. The mistake people make, and well-intentioned high school, and I'm sorry to say some faculty here at Santa Fe, the mistake they make is to omit the change of the bounds from a to b to g of a to g of b. So first I'm going to show you some examples. Then I'm going to show you a bunch of pictures and try to convince you that this is really important. And then we're going to do more examples. Let's start easy. Let's go from 0 to pi and say sine of 3t dt. Oh, yeah, that's fine. So just like with our substitutions the other day, I want to try to visualize the integrand as like an outer function and an inner function. And then I'm going to substitute for the inner function. So here I'd want to sub u equals 3t. I calculate the differential du before doing anything else. That would be 3 dt because the derivative of 3t is just 3. The other really important thing here is that we remember to change the bounds. So when I do this, I like to write it like this. My old bounds go here. I put the lower bound down low and the upper bound up here. And then I draw a little arrow. And I'm going to put the new bounds over here. Now these new bounds are going to be values of the variable u. So this 0 and that pi, those are t values, right? Those are values for this guy. And this is a dt integral, so those bounds are t values. When I make the substitution, I'm going to be changing it into a du integral, so these guys are going to be u values, right? U is g of x. The way you get the new bounds is very simple. You plug the old bounds into your substitution. That's it. So when t is equal to 0, what is u? Well, u is 3 times t, so 3 times 0 is 0. When t is equal to pi, what is u? Well, u is 3t, so when t is equal to pi, this is going to be 3 times pi, or just 3 pi. Now this notation is a little cumbersome, so I might truncate it a bit as we move forwards, but this is what's going on. And I'm going to say this a bunch of times today, but every time you substitute in a definite integral, what am I doing there? Definite integral, you must change the bounds. Okay. Everything else goes exactly the same as it did with indefinite integrals. So I'll write the original problem here, integral 0 to pi, sine of 3t dt. This is going to become the integral from 0 to 3 pi of sine of u. And then if du is 3 dt, then 1/3 du is dt. So this will be times 1/3 du. Now remember, we talked about a few ways to handle the differential. You can either solve for the original differential and just plug in, or you can try to manipulate the integrand to get whatever's here to show up here. So I could multiply by 3/3 and then say the 3 dt is du, leaving the 3 downstairs. Either way is fine. The 1/3 is a constant factor. So I'm just left with 1/3 integral from 0 to 3 pi of sine of u du. If you wanted to, we could at this stage make some symmetry arguments, but it's not necessary. You know an antiderivative for sine of u is negative cosine of u. And we do not write a plus c here, just like before when doing a definite integral, there's no need to write the plus c. Here's the other place where I differ from those overzealous high school and Calc 1 teachers. You don't need to plug back in the original variable. With indefinite integrals, you do need to plug back in the original variable because the answer there is a function, and that function should be a function of the same variable that the problem was stated in. Here, though, I'm just asking for an area. And because we changed these bounds, we can evaluate this antiderivative between these new bounds without ever plugging back in 3t. So this is 1/3 times negative cosine of 3 pi minus negative cosine of 0. Which is 1/3 times, let's see, the cosine of 3 pi. What is that?
-1.
Very good, right? That's like walking around the unit circle 1.5 times. So this is -1, which is +1. I'll just write it like that. Minus the cosine of 0 is +1, so this is minus -1. So we end up with 1/3 times 2, which is 2/3. Just one more. What the hell is going on out here? Okay. So the procedure isn't all that radical, but there are a few things that may differ from stuff that you've heard elsewhere. The note I want to make here is, since we changed the bounds, we do not plug back in 3t for u. And that's it. Those are the two kind of differences between the way I encourage you to learn this stuff and the way some other people teach it. Some people say, don't change the bounds and then plug back into the original variable. Having shown you that you don't need to do all that shit, that you should change the bounds and that you don't need to plug back into the original variable, I want to convince you why. And to that end, I want to look at the definite integral version of, let me see. Let's do this from 2 to 5. I'm going to start by looking at the graph of this function. All right, I'll run you through the procedure here in just a second, but for now, I just want you to think along with me. I'm going to rescale my y-axis. No, that won't get this out of the way. Should hide that later. So y-axis is something. All right, and we'll say 0 less than. All right. So here's this curve. And the definite integral that we're trying to compute, the integral from 2 to 5 of that function, is this blue area here. Just hold on to that in your brain. The substitution here, we looked at a problem like this the other day, is going to be for the radicand, the thing under the radical. We're going to sub u equals x minus 2, which means that du is the same as dx. When x is equal to 2, u would be equal to 2 minus 2, which is 0. And when x is equal to 5, u would be equal to 5 minus 2, which is 3. So this will be the same as the integral from 0 to 3. We'll have a square root of u from the radical. dx and du are equal to one another. And remember, the trick to deal with that leftover x was to add 2 to both sides, to go back to your substitution and solve it for x. So that means u plus 2 is equal to x. So it goes in here as u plus 2. Before I return to Desmos, are there any questions about where this integrand is coming from? Why we have a u plus 2 and a square root of u there?
If you don't mind explaining it real quick.
I'm sorry, say that one more time.
I'm sorry, if you don't mind explaining it real quick.
Sure.
Thanks.
So since x minus 2 is equal to u, this piece will be the square root of u. Because du and dx are equal to each other, I don't need to do anything special here. Dx is just du. The challenge is this guy. So we know that we need to replace every instance of the old variable by the equivalent expression in terms of the new variable. In other words, we've got to replace all the x stuff by its equivalent form in terms of u stuff. So after we plug in the kind of obvious pieces like square root of x minus 2, that's going to be the square root of u because we sub for the inner function. We chose to sub for x minus 2. So this piece definitely becomes root u. That's kind of the decision we made. When we calculate the differential du, we found that it was equal to dx because the derivative of x minus 2 is just 1 minus 0. So du would be 1 dx. The lingering piece here is this x. And the question is, well, what the hell do I do with that? I know I can't just leave it as x because we have this rule that says we need to get all the old stuff in terms of the new variable. And the trick is to go back to your substitution, which we chose to substitute u equals x minus 2, and to solve that for x. And then whatever I get when I solve this for x, I know I can plug that in here. In this case, it's not too hard to solve for x. We just add 2 to both sides. So if u is x minus 2, then u plus 2 is equal to x. So this x I can replace with u plus 2. So now what I'd like to do is to look at this guy, but pretend that we didn't change the bounds. Let's say, I'll just write y equals. The green curve and the red curve are very similar. The green curve has just been slid over to the left. Let me go ahead and call this G of u. Now, if I leave those bounds alone, well, why is it insisting on a slider? No. Ah. Right. Maybe this will work. Yeah. Okay. So let me make some color changes here. Let's call this green. Let's call this red. Okay. Yeah. So the green area here is what we would get if we did this integral from 2 to 5. But what I want is the red area down there, right? This red area is what I'm after. The green function, the green curve, is what I get when I perform my substitution. The substitution u equals x minus 2 basically drags the whole graph to the left by 2 units. So what I need to do is also drag my bounds to the left by 2 units. So if I do this integral from 0 to 3, now you see the green area and the red area are the same. And that's what we want. I want to say that this integral is equal to the integral I started with. It would be incorrect to say that this integral from 2 to 5, if I didn't change the bounds, is equal to this. That would be a lie. So the comment here integral from 0 to 3 of u plus 2 square root of u du is equal to the integral from 2 to 5 of x square root of x minus 2 dx. But the integral from 2 to 5 of u plus 2 square root of u du is not. So we really do have to change the bounds. When we're making a substitution, what we're doing is in these simple substitutions like this, like u equals x minus 2, we're just dragging the graph to the left or to the right. We saw on Monday that sometimes the substitutions we make are a little bit more complicated, where du and dx are not just straight up equal to each other. In those cases, we're not just dragging the graph to the left or the right, but we're also stretching out parts of the graph. And we might be stretching out certain parts of the graph more or less than other parts of the graph. So a substitution is a coordinate transform. That's what's going on. I'm changing from the xy plane to the uy plane. And in order for the area measured by this integral to be the same as the area measured by this integral, I need to adjust the bounds. Because like we said over here, if I found the area under the green curve from 2 to 5, that's much bigger than the red area. But if I find the area under the green curve from 0 to 3, that is the same as the red area. And that's what we want. There is a web page that goes into detail about the slightly more complicated transformations. Let me see here. I know I have it in the Calc 2 modules. I think I have it in yours as well. But just in case, I'll paste it into the chat here. So they use a similar example, and they justify it in the same sort of way by saying, think about the area under here and think about the area under here. But they do a good job in something else also. And this is something that's very hard to draw by hand, so I'm not even going to try to communicate this here. But what the dx term signifies is how much you are stretching or shrinking the x-axis when you do the transformation into the u-axis. So in the example they're looking at here, they're going to make the substitution u equals x squared because of this x squared here as the inner for the exponential. And when you do that, du is equal to 2x. So this piece is going to go away, and you get an easy thing. But what we need to do is try to understand what that transformation is doing graphically. So graphically, what that's doing, here's the graph of the original function, and here's the graph of the transformed function. And in order for the area bounded by the first one to be the same as the area bounded by the second one, we have to imagine this as stretching the x-axis out a lot over here to the right of 1, and compressing the x-axis in here between 0 and 1. Because that's what the squaring function does. If you take a number between 0 and 1 and you square it, it gets smaller. Think like 1/2 squared is 1/4. If you take a number larger than 1 and you square it, it gets bigger, like 2 squared is 4. There's one other really good resource for this. I think it's in his Essence of Calculus video. This is it. I'm definitely not going to play the whole thing. I'm just going to find the timestamp for you, and I'll put it in the chat as well. This guy's channel is wonderful, by the way. Very, very nice math stuff.
Derivatives, which I'll refer to as the transformational view, it generalizes more seamlessly into some of those more general contexts where calculus comes up. And then we'll use this alternate view to analyze a certain fun puzzle about repeated fractions. But first off, I just want to make sure that we're all on the same page about what the standard visual is. If you were to graph a function, which simply takes real numbers.
These two resources, I think, are very nice for actually understanding what it is that's going on when we make a substitution in an integral. And I strongly encourage you to check them out. With all of that grandstanding done, let's get some more practice, because we know there's lots and lots of challenging integrals out there in the world. Let's see if we can do some of them. All right. We can start. We can start there, that's fine. Sure. Let's evaluate the integral from 0 to 1 of the cube root of 1 plus 7x dx. So I want you guys to tell me what to substitute, and we'll walk each other through this. What would be a good choice of substitution here?
One plus 7x.
Very good. Yeah, we want to sub for the inner function. Maybe I'll go back to using different letters here to try and get us comfy with that. So I'll let z be 1 plus 7x. Which means that dz, if I take the derivative of 1 plus 7x, I just get 7. So dz is 7 dx. What this means, by the way, is that in terms of the transformation, I'm not just shifting here. I am doing a shift, but I'm also stretching the x-axis out by a factor of 7. And you'll see that reflected when we change the bounds. When x is equal to 0, z would be 1 plus 7 times 0, which is 1. And when x is equal to 1, z would be 1 plus 7 times 1, which is 8. So the two things going on with this substitution, the coordinate transform here, we're moving to the right by 1 unit, and we're also stretching out by a factor of 7. I'm taking the interval 0 to 1, and I'm transforming it into the interval 1 to 8. When we do this, the integral 0 to 1, cube root 1 plus 7x dx, my original integral, is going to become the integral from 1 to 8 of the cube root of z, and then the dx is going to be 1/7 dz, right? If I divide both sides by 7 here, I get 1/7 dz. So a factor of 1/7 can come out. And what's left is the integral from 1 to 8 of the cube root of z, which I'll write as z to the 1/3 power. The 1/7 is still just going to hang out front. my antiderivative for z to the 1/3, we add 1 to this. So 1/3 plus 1 is 1/3 plus 3/3 is 4/3. So this will be 3/4 z to the 4/3, right? We add 1 to the power and then divide by that power. Dividing by 4/3 is the same as multiplying by 3/4. And this needs to be evaluated from z equals 1 up to z equals 8. We can pop the 3/4 out if we want. That'll give me 3/28. And then inside here, I'd just have z to the 4/3. So that'll be 8 to the 4/3 minus 1 to the 4/3. So there's a few big steps here. Are there any questions about how we go from any one piece to the next? Okay. Then let's try one more kind of at this level, and then we'll step it up a bit. Let's do the integral from 2 to 6 of 1 over 3x plus 1. Can anybody recommend a substitution here?
Oh my gosh.
3x plus 1.
Very good. Yeah, I'm thinking of the outer function as being like 1 over u, and the inner function is the 3x plus 1. So I'd sub, oh, my pen died. U equals 3x plus 1. What is du going to be?
Three dx.
Yeah, 3dx. Yep, exactly. So we take the derivative of 3x plus 1, that is 3, and then we slap on a dx. Sorry, I misheard you at first. I thought you said 3 to the x, and I was thinking, I don't know, but just my brain. All right. We change the bounds. When x is equal to 2, u would be equal to 3 times 2 plus 1, which is 7. And when x is equal to 6, u would be equal to 3 times 6, which is 18, plus 1, which is 19. And then the only other thing, I didn't write it out explicitly last time, but 1/3 du would be equal to dx. And that's what we're going to replace this dx by, is 1/3 du. So under this substitution, my integral is going to become the integral from 7 to 19 of 1 over u times 1/3 du. And that 1/3 is a constant. He will come out. And I'm left with the integral from 7 to 19 of 1 over u du. And we've run into this enough now that we should be comfy. What is the antiderivative I will use here?
ln of u.
Yeah. If we're being careful, we should put absolute values here. But that's correct. It's the natural log of u, or the natural log of the absolute value of u. If this was going from -7 to -19, I could still do all of this, and there I would really need the absolute values because the natural log isn't defined when you plug in negatives. But this works. And then we'll have the natural log of the absolute value of 19 is just 19. So we'll have natural log 19 minus similarly natural log of 7. So the absolute values really only matter if you're doing an indefinite integral or if in a definite integral your bounds are negative. But it's still nice to be in the habit of writing the absolute values, and then you can omit them if your bounds are positive in the next step.
So
So
do you
even
always
if-
write an, sorry.
Oh, go right ahead.
So do you always write an absolute value when you take the integral of 1 over u or 1 over x?
Yep. Yeah, I do. It's the right habit to be in because it is the more general antiderivative. It is true, right, that the derivative d du of the natural log of u itself without the absolute values, this is equal to 1 over u, but only if u is positive. If u is negative, then this function isn't even defined, right? But the catch is this function is defined if u is negative. So what I'd really like is an antiderivative, something that could go inside here, that works not only when u is positive, but also when u is negative. And we went through a little bit of this proof when we were back in 4.9. If you differentiate natural log of absolute value of u, this is also equal to 1 over u. And this is for all u not equal to 0. So the natural log of the absolute value is the more general antiderivative. They both work. It's just that this, right, the 1 over u only works if u is positive. This, with the absolute values here, works whether u is positive or negative. The only time this doesn't work is when 1 over u is itself undefined at 0. So I like to always be in the habit of saying the integral of 1 over u du is the natural log of the absolute value of u. And you know, plus c if we're talking about indefinite integrals. So anytime I'm integrating 1 over u or 1 over x, I always write the absolute values, at least in the first line. And then if the context of the problem, you know, makes it clear that you don't need the absolute values, like here we're going from 7 to 19, those are all positive numbers, then I can get rid of the absolute values in the next line. But just to make sure that my reader knows what I'm doing and what I'm applying, I think it's nice to do. Also, it shows me on your test that you remember that the absolute values belong there. There are cases where you could omit them, but if you want to make sure you're always correct and don't have to worry about it, just use absolute values. You may remember last time when we did the integral of tangent and the integral of secant, those both involve natural logs. And the insides there were trig functions. And we know those are positive, negative, all over the place. So the absolute values in that sort of setting are very important. Speaking of trig functions, let's do something with these guys. Let's look at.
Quick question.
Sure.
We're just leaving it in this instance as like 1/3 times natural log, etc. But like in reality, we're expected to complete it.
Well, there's really not much more to complete here. The only thing that you could do is combine these into a single natural log, 19/7. But there really isn't anything else. I mean, if you wanted to, you could bring the 1/3 in. You could write this as the natural log of 19/7 to the 1/3. But yeah,
But we
this-
won't have to like plug it into a calculator or anything.
no, in fact, I would way prefer this over a decimal. Yeah, this is exact.
Okay,
The decimal is just an approximation.
thank you.
Yeah, no problem. All right, let's look at something tricky. Let's do. This can be done a few different ways. This does not necessarily require a substitution. You could treat this as secant times tangent, and we know an antiderivative for that, but it can also be done as a substitution. So let's see how it comes out if we choose to sub. What might we try substituting for here? You know what? As a matter of fact, let's mandate the substitution. Let's make this a cos cubed. So integrate from 0 to pi over 3 sine x over cos cubed x. Now you need the substitution. Maybe changing that tells you a little bit what to sub for.
Cosine x.
Yeah, definitely cos x. So if I let u be the cosine of x, then du is going to be the negative sine of x dx. And before I go on, I want to talk for just a second about orientation. The fact that there's a negative showing up here in the differential, we talked about like what a 2 dx does. That's stretching out the graph, stretching things out by a factor of 2, stretching horizontally by a factor of 2. What the negative does here is it flips the interval over. It's kind of cool. So if your differential has a negative in it, that means that the orientation of the integral is going to be reversed. Instead of going from left to right, after we do this, we're going to be going from right to left. And we'll see what effect that has after we implement the sub. So when when x is equal to 0, u would be the cosine of 0, right? Because u is cosine of x, and that is 1. When x is equal to pi over 3, u would be the cosine of pi over 3. Can anybody remind me what that is?
One half.
Yeah, very good. That's 1/2. So then my integral 0 to pi over 3 of sine x divided by cos cubed of x dx is going to be equal to integral from 1 to 1/2. Downstairs here, cos cubed is going to be u cubed. The sine x here, I can group with the dx here. So I've got a sine x dx. And this negative, I can move over here. So this is going to be -1 du. And again, you could do this the other way where you solve this for dx, right? Dx would be du over negative sine x, and then the sine x's would cancel and you'd just have the -1 factor. If you want to think about it like that, you can, that's okay. Just remember, you cannot do any calculus or integration until all the x's are gone. So I want to hold here for a second. This one's a little more complicated than the last. Are there any questions about how we get to this step?
So the sign on top got canceled out by, wait, no, my hand is confused. Sorry.
Yeah, so let me play with this over here. Sometimes if you want to see it from this angle, it can be helpful to rearrange the integrand a little bit without plugging in the substitution. So I can write this as cos cubed x times sine of x dx. And that's the same as the integral from 0 to pi over 3 of -1 over cos cubed x times negative sine of x dx. So now here I have my negative sine of x dx. And this is going to become my -1 over u cubed. So if you,
Thank you.
yeah, no problem. We can do it like this, or you can solve for dx. I might as well. No, I'll leave it like that. We'll do one more that's in that other style. So then from here, I'll pop out my -1. I have integral 1 to 1/2 of 1 over u cubed du. Now that's kind of unsatisfying, isn't it? What's unsatisfying about the way this is written right now?
The u cubed.
I suppose that's more a matter of taste. There's something here that bothers me.
Can you switch your bounds and make it positive so then the bigger one's on top?
Yeah, the bigger numbers usually up here and the smaller numbers usually down here, right? It feels weird to say I'm integrating from 1 to 1/2. And that's what I meant when I said it's an orientation reversing integral or orientation reversing substitution. This has me walking from right to left rather than from left to right. This says you're going to integrate starting at 1 and move over, from your perspective, over to 1/2. And that's not usually how we talk about this, right? We usually talk about going from 0 to 5 or 1 to 10, going from a smaller number to a larger number. And the fact that we get a negative from this differential, which gives us the negative here, is precisely what we need to flip this over. So remember the rule. Let me finish writing this down. This is, I'll write 1 over u cubed as u to the -3 du. And the rule is that the integral from a to b is the negative of the integral from b to a. So you can flip your bounds and it'll soak up a negative sign. Or if you wanted to, in the other direction, you could flip your bounds and it'll pop out a negative sign. The idea is that you can, changing the bounds negates the integral. From here, life is gravy. I can integrate u to the -3 using my power rule. So that would become u to the -3 plus 1 is -2 divided by -2. No plus c because it's a definite integral. Evaluate from 1/2 to 1. No need to go back to the original variable because I changed my bounds like a good math student. I do want to make this a little prettier before we go plugging stuff in. So there's a -1/2, that's the -2 downstairs. And then u to the -2 is 1 over u squared. And it might seem cumbersome or extra to do this, but I think it is worthwhile. And that then will give me -1/2 times 1 over 1 squared minus 1 over 1/2 squared. One squared is 1, 1/2 squared is 1/4. So this is -1/2 times 1 minus 1 over 1/4. As unsatisfying as that is to write, I will write it for now. 1 divided by 1/4, though, that's 4. One minus 4 is -3. That's -1/2 times -3 is +3/2. questions on this guy? Okay, let's chew on a few more of these and then I'll let you go. What looks hard? You tell me, what looks hard? What from this list of definite integrals over here, what would you not want to see on exam 3?
70,
70? Let's do it.
72.
Oh, 72. Okay. Sure. We've got a lot of kind of arbitrary looking symbols floating around here. Let's get this written down. We're going to integrate from 0 up to capital T over 2, the sine of 2 pi little t divided by capital T minus alpha d little t. So I would write it like this. Remember your order of operations, the division is definitely higher in the hierarchy than the subtraction. So it's 2 pi little t over big T. And then that minus alpha, that's not a part of the downstairs, that's separate. So it's like this fraction minus alpha. Bunch of confusing looking things here. The fuck is this? The fuck is this? Don't be scared. Just think about the same ethos that we've applied through all the other substitution problems. Here's an outer function. Here's an inner function. Sub for the inner. So u is going to be 2 pi t over cap t minus alpha. Taking the differential here looks like it might be hard, scary, whatever, but it's really not because the capital T is a constant. I'm going to take up some extra space here to write this as 2 pi over capital T times little t minus alpha. Remember, we can always do this. Having something multiplied upstairs is the same as having that thing multiplied outside the fraction. So now this is just looking like a constant times t minus a constant. So du is just 2 pi over cap t dt. Right? This is a constant multiple. So like 5t differentiates to 5. 2 pi over cap t times t differentiates to 2 pi over cap t. Alpha, this is a constant. He differentiates to 0. So your differential is just this.
So the alpha doesn't count as a variable.
Correct. Yeah, unless you're told otherwise, unless you're told that alpha or capital T somehow depend on little t, then you can assume that all the other symbols are constants. And that's true for all the problems like this. I think I gave you one of them in your homework that has this feel, where you've got like an A, or there's one with a B somewhere. Unless they tell you otherwise, assume anything other than the thing with the differential at the end is a constant. So in this one, we have a dt at the end. That means like little t is the variable, everything else is constant. Okay. I need to change my bounds also. I closed my little substitution box there. That was a mistake. I shouldn't have done that. When little t is equal to 0, u would be negative alpha, right? If I plug in 0 for t here, I get 2 pi over big T times 0 minus alpha. So that means u would be negative alpha. And when little t is equal to big T over 2, u would be equal to, well, what happens if I plug big T over 2 in here? Maybe we'll do it. This is going to be 2 pi over big T times big T over 2 minus alpha. which is, I'll do it up here. You can cancel the 2's, you can cancel the t's, and you get pi minus alpha. So my new integral is going to run from negative alpha up to pi minus alpha. I'll have the sine of this stuff, the sine of u. And then my differential, fit that in here. If we solve this for dt, we get big T over 2 pi times du is equal to d little t. So I have big T over 2 pi du, that I will replace dt by. Really not too scary. Not too scary, just lots of extra symbols. Again, big T is a constant, pi of course is a constant. So big T over 2 pi comes out. Integral negative alpha to pi minus alpha. Sine of u du remains. Antiderivative for sine would be cosine. So this is big T over 2 pi times, oh sorry, negative cosine of u. And we evaluate this between our new bounds. We do not plug back in. We do not use the old bounds. We change the bounds. We use the new bounds. Evaluating, I get the negative cosine of pi minus alpha minus negative cosine of negative alpha. And although it's not immediately obvious, there's quite a bit we can do to clean this up. If you gave me the above answer as your answer on a test, I would say that's wonderful. 10 out of 10. But we could also do this. Minus minus here makes plus. And there's two other things we can do. One of them I think is fairly obvious. The other one is certainly less obvious. The more obvious one is that cosine is an even function. So the cosine of negative alpha is the same as the cosine of positive alpha. And the definition of an even function is that f of negative x is the same as f of positive x. So cos of negative alpha is the same as cos of positive alpha. Again, not required to get full credit on the test, but a nice thing to know. The other nice thing to know here is that cosine and sine are out of phase by, well, let's see. Let me look at this, this, and this. First off, isn't that pretty? Second. What's the relationship between the Christmas colors?
Shifted by pi.
Shifted by pi, yep. And for sines and cosines, shifting by pi is equivalent to vertical reflection. So the cosine of pi minus x is the same as negative cos of x. So cos of negative alpha is the same as cos alpha. Cos of pi minus alpha is the negative of cos alpha. So I've got negative, negative. So this is t over 2 pi times cos alpha plus cos alpha. Which is 2 cos alpha. So finally, you can cancel the 2's, and this is t over pi cos alpha. And just because I don't want to scare you, I want to reiterate, on the test, if you give me this 10 out of 10, perfect score, good job. But these properties of sine and cosine, these really neat geometry properties are special. And I think it is at least a little bit surprising, if not beautiful, that this is the same as this. Integrals like these show up when you study what are called Fourier transforms, of Fourier series as well. The 2 pi over t alters the period. That changes the period of the function to t. So what we're doing is we're asking what happens in general if you take a period t sine wave, give it a horizontal shift of alpha, sometimes called a phase angle alpha. So you take a period t sine wave with phase angle alpha, and you integrate over a half period. Fourier transforms, Fourier series, very important in signal processing. All right, I think we have time for one more. What else looks scary?
How about 70?
70? Okay, yeah, these two, 69 and 70, I like both of those a lot. So here we have the integral from 0 to 2, x minus 1, e to the quantity x minus 1 squared dx. This is a problem that I think a lot of people, especially when they first meet it, might do in 2 substitutions, and that's not uncommon. Certainly I see an x minus 1 and an x minus 1. I have an outer function here that is like u e to the u squared, where u is the inner x minus 1. So there's 2 paths. You could sub something like u equals x minus 1, du equals dx, and whatever the appropriate work is for the bounds. Then sub w equals u squared, dw equals 2u du, and whatever the appropriate work is for the bounds. And I think the first time you attack a problem like this, that's a very reasonable thing to do. I invite you to try solving it that way. I'm going to do something a little bit different. We can get it done in a single shot by subbing u equals quantity x minus 1 squared. Sub for the inner here. Because the differential is going to be 2x minus 1 dx by the chain rule. Right? The derivative of x minus 1 all squared is 2 times x minus 1 to the 1. So that differential is 2 times quantity x minus 1 dx. changing the bounds, when x is equal to 0, u is equal to 0 minus 1, which is -1 squared, which is 1. When x is equal to 2, oh, this is interesting. Hang on. Yeah, something funny is going to happen here. When x is equal to 2, this will be 1 minus 1 squared, which is also 1. So let's go ahead and write down the result. This would tell me that my new integral is the integral from 1 to 1. This x minus 1, let me back up. Let's rewrite the original integral. We've got 0 to 2. I'll have my e to the x minus 1 squared. And I'm just going to put the x minus 1 over here with the dx to make it a little easier to see what we're going to do. So this x minus 1 dx, I can think of as this x minus 1 dx. So 1/2 du is x minus 1 dx. So this piece will become 1/2 du, and this will be e to the u squared. So I would have the integral from 1 to 1, e to the u squared times 1/2 du. Do I want to continue with this? Is there anything else I need to do? Oh, sorry, not e to the u squared. I'm so sorry. Just e to the u. Just e to the u. We're subbing u equals x minus 1 squared. Yeah, so this whole thing is u. Let me annotate here. I've made it confusing. This piece is e to the u because u is x minus 1 squared. And this piece is 1/2 du. All right, so I apologize. This is not e to the u squared. This is just e to the u, right? Because this piece, this whole thing here is u. We can go ahead and calculate an antiderivative and plug in bounds. This would be 1/2. Antiderivative for e to the u is e to the u, and then I evaluate from 1 to 1. That's 1/2 e to the 1 minus e to the 1, which is 1/2 times 0, which is 0.
Do you have to go that far to show that integral from 1 to 1 is 0?
Very good. No, you do not. That's what I was going to ask. So as soon as you calculate these new bounds, right? When I said, do we want to keep going here? As soon as you calculate these new bounds, you should be able to deduce that the integral is 0. Because immediately at this point, we realize that under this transformation, my integral is going to become an integral from 1 to 1. So the nice observation there was, I think that came from Ethan, was that we could stop here. Integral 1 to 1 of anything automatically 0. Integral from a to a of anything is always going to be 0. If the upper and lower bound are identical, then you will always get 0. The only place you need to be careful about this sort of stuff is when you're working with trig functions. Due to the periodicity of trig functions, when you substitute for a trig function, sometimes you can get the upper and lower bounds appearing to be the same thing, even though the original integral ought not be 0. An example of this I saw recently was what was it? And this was being done, I think, originally from 0 to 2 pi. This is a case where you can get integral. I'm not going to do this, we're out of time. But the procedure for this, after some amount of work, leads you to integral 0 to 2 pi sine of x over the square root of 1 minus cos of x dx. And I think there's a 2 over the square root of 2 out front. It's just algebra to go from one to the other. You multiply by the radical of 2 minus 2 cos x. If you make the natural substitution from here, which is for 1 minus cos x, then you're going to get the integral from 0 to 0, which is incorrect. This integral is not 0, right? This original integral is not 0. This isn't something you're going to encounter in Calc 1. Like I said, this is something that one of my Calc 2 students brought to me in office hours today, and we had to stare at it for a minute to figure out what the hell is going on. So I'll say this. If you make a substitution and your bounds come out the same, first, in this class, yeah, you can go ahead and assume it's 0. In real life, in later classes, what you'd want to do is take at least a cursory glance at the graph to make sure what you're saying makes sense. So if I were to evaluate this guy from where are we going, 0 to 2?
I think you have an extra negative in the exponent.
Yeah. Thank you. That's right. Oh, maybe we have run into something like this here as well. Let's see, 0 to 2. Minus 1 squared. Yeah, 0. Oh, it's not, for some reason, it's not showing the area here. I see what's going on. I see what's going on. Oh, and it doesn't like that either. So that's not why. Can I get it to do this? No. All right, here, give me 1 second. 0 less than x less than y. No. What is it going to be? Yeah, there it is. All right. So here's the area we're calculating, right? It's the black and the purple together, and they cancel. The two purples here now, as I've drawn them. This guy is indeed the negative of this guy. So we do expect to get 0 out here. So when you do run into that, where you make a substitution and your bounds become the same, basically, if you're not dealing with trig functions, you're safe. If you are dealing with trig functions, take a look at the graph. And if you're at all uncertain, take a look at the graph. There's no harm in it. I'll tell you what I did in my head when I saw this was I tried to think about the symmetries of this guy. So if you're to do the sub u equals x minus 1, this first simple substitution, then this would become x times e to the x squared. And the x term would be negative from -1 to 0. Or equivalently, the x minus 1 term would be negative from 0 to 1. So this function is symmetric about the line x equals 1. You see that here? We have this axis of symmetry. We're negative to the left of this line, we're positive to the right of this line, and the graph is perfectly symmetric about that line. So any area over here will be canceled by the area over here. If you can spot those sort of symmetries looking at the algebra, that's great. But I would say just proceed like normal, make the substitution you think you should. And if you get something like this, which is like super quick simplifying, like making the whole thing 0 without any work, maybe take a look at the graph. If you're uncertain, definitely take a look at the graph. It couldn't hurt you, or try to train yourself to recognize symmetries. What I'll be testing you for on the exam is the ability to execute the procedure. So do you understand what substitution is and how it works? Can you make it go? Can you turn the crank? I'm not going to be trying to fool you with anything like this, but it is a nice thing to observe, and it's good to know. It's good to save some time, right? That's all. It's just a nice observation. Okay, that's all I have for you guys today. I've taken up enough of your time beyond class. Is there anything burning in your brains that you would like to ask before I let you go?
What day is the test?
We took a poll in this class, right? And you guys opted for the Wednesday, is that correct? Or for the Friday? Honestly, I'd have to look back at the
I
video.
think it's Wednesday, the 20th.
Yeah, I thought you guys went for the Wednesday as well. So Wednesday, the 20th, 1 week from today.
And the study guide?
I will go ahead and release your study guide today. I'm working on the Calc 2 one right now, so I'll swap over to yours and get that out by 5 or so. Any other burning questions? Okay, then I will go ahead and end the meeting here. I hope you guys have a lovely afternoon. Work hard on that homework, and I'll see you on Friday.